First of all, we're going to talk a bit about what we call concavity. We know the derivative measures a rate of change in something. So the first derivative measured the rate of change of the y with respect to x, and we called that a slope. Now the second derivative is when we differentiated the first derivative. So in other words, we're finding the rate of change of the first derivative. So when we talk about a graph, we talk about the rate of change of the slope. Now that's what we call concavity. So concavity measures the rate of change of the slope. So if our second derivative, which is measuring concavity, is greater than 0, the curve ends up being concave up. Because what we're saying is the rate of change is positive, so the slope is getting more positive. Well, look at a curve that's concave up. It's this parabola here, starting with a slope of, I don't know, let's say it's -2. And then it comes down, it gets to 0, but now it starts getting positive. So it's getting more positive as we go from left to right. So its second derivative, its rate of change, is positive. So similarly, if the second derivative turns out to be negative, then the slope must be getting more negative as we go along, so we get a concave down curve. That leaves us with the option equals 0, and it's a possible point of inflection. Might not actually be one, and we'll talk a bit more about that later. So this time we're going to draw a sketch just looking at the second derivative. What would this particular polynomial look like? So we'll differentiate it once, differentiate it twice. So I'm just going to look at the second derivative, and all I know at this stage is I can use it to say concave up or concave down. So if I look for concave up, when is this greater than 0? Well, that'll be when x is greater than -5/3. So I know when it's greater than -5/3, I have a concave up curve. Logically, if it's less than, I must have a concave down curve. So it would look something like this. Well, -5/3, again, I haven't exactly worked out where the x-intercepts are and things like that, but it would have that sort of shape. So that's just drawing the graph only using the second derivative. Yesterday, we looked at drawing graphs only using the first derivative. So if we now combine the two together, we get something a little bit more powerful. Turning points, for instance. Okay, we can use the first derivative to find stationary points. We said that's when the first derivative was equal to 0. But then we can use the second derivative to now go and classify them. We don't need to draw the table of values, because we're saying we've got a stationary point, but now we're also saying the curve is concave up. So if we're concave up and stationary, I must be down the bottom. It's a minimum turning point. If it's less than 0, so it's concave down and stationary, then I'm at the top, must be a maximum turning point. Now that doesn't mean the table of values is not a useful idea. It's still a useful idea, because if you've got a function that's difficult to differentiate, like you'll differentiate it once to find the stationary points, but do you want to go to the trouble of differentiating it a second time? No, it's probably easier just to use the first derivative and look either side. Polynomials, of course, it's going to be real easy to find second derivatives of, so we'd use that every time. We wouldn't use table of values. So let's find the turning points of this polynomial. Well, I'm going to need the two derivatives. So there's our first one, there's our second one. So the first thing we do is we try and locate the stationary points. Again, make sure you write this information down. Explain your solution. I know stationary points are going to occur when the derivative is equal to 0. So I want to solve this quadratic. Comes up with two possibilities, a third and -1. But now I'll go and classify. So when x is -1, I substitute it in, it's -4. The 4 I'm not that interested in, it's the negative I'm interested in. That tells me it's concave down, so I must have a maximum turning point. I suppose the -4 tells me how quickly that slope's changing. So the bigger the number, the quicker that slope is changing. Okay, let's do a third. Subbing a third in, we get +4. Now, just a coincidence, it ends up being the same number, but that's positive. So we have a minimum turning point. So probably quicker than our table of values for this one. But these things called inflection points, what are they? I said that it's when the second derivative was equal to 0. So this is where it possibly might change in concavity, because if you're going to change from positive to negative, then somewhere you've got to have 0 in between. So this will locate our possibilities. So we can do a similar thing. If I want to find the inflection points, dy dx, there's my second derivative, 24x plus 12. So again, I will write down what I'm attempting to do here. Well, I know possible points of inflection. Make sure you include the word possible, because it might not be a point of inflection. These are possibilities we're looking for. And we come up with one possibility, x equals minus a half. Now, logically, it must be an inflection point, because we're talking about a polynomial, which we know is a continuous curve. It would end up having two stationary points, because there's my quadratic. One will be a minimum, one will be a maximum, so logically, somewhere in between there must be an inflection point. That's not good enough for a proof, though. So let's have a look either side of our second derivative, similar to what we did with the first derivative yesterday. I know at minus a half, it has no concavity. I'll pick a point on the left-hand side and on the right-hand side. On the left-hand side, I've gone with -1. Sub that in, I get -12, concave down. Positive side, I've used 0, and I end up with 12, concave up. So yes, there is a change in concavity. In your solution, make sure you include that statement, because you're letting them know that you understand inflection points are a change in concavity. So write it in there. Yep, therefore, there's a change in concavity. Well, if there's a change in concavity, that must be a point of inflection. A horizontal point of inflection is a very special point of inflection. It's an inflection point that is also a stationary point. So the classic one being our cubic at the origin there. So at the inflection point, the tangent would be horizontal. That means the first derivative would be equal to 0. The second derivative would be equal to 0. And the third derivative won't be equal to 0. What? The third derivative? Let's now take a journey outside the syllabus. Do not know why it's not mentioned in any textbooks or anything like this. It's crazy because this is easier. Here's a different way of finding inflection points. Oh, and by the way, you might want to tell your tutor about this too, because they usually don't tell you either. We've said possible points of inflection occur when the second derivative equals 0. So we've still got to locate the possibilities. But this is what happens. If the first non-zero derivative is of odd order, so the third derivative, the fifth derivative, seventh derivative, whatever, then it is a point of inflection. By far, the majority of the functions we're going to look at, it'll be the third. If the first non-zero derivative is of even order, fourth, sixth, eighth, and so on, then it's not a point of inflection. So the example we just did, the third derivative would be 24. Well, 24 is not 0. So therefore, there is a change in concavity. It's a point of inflection. Hang on. Why does that mean there's a change in concavity? The derivative measures rate of change. The second derivative measures the rate of change of the first derivative. Therefore, the third derivative measures the rate of change of the second derivative. Well, we want to see if there is a change in the second derivative. Therefore, if it comes up with any value other than 0, there must be a change in concavity. The only way it's not is if it's 0, because we're saying, no, there's no change in concavity. So you just use the third derivative. Jolly good fellow.